Imagine you are designing a drone and it starts oscillating uncontrollably. Or think of a car cruise control system that keeps speeding up instead of stabilizing. These are problems that happen when systems are unstable. Today, we Group 2 members offering biomedical engineering any year 3 are here to solve a classical control problem to determine when it's stable and when it's not.
Control systems are very important in biomedical engineering because many medical devices should operate safely and precisely. So, for example, you take an infusion pump, it delivers medicine to the patient's body at a controlled rate. So, if the system is unstable, it could deliver too much or too little medication, which can be dangerous and lead to complications. So there's a need for a control system to ensure steady flow rates of the drug to the patient. Another example is the pacemaker. The pacemaker monitors the heart's rhythm and sends electrical signals when needed to maintain a stable heartbeat. So if the control system inside the pacemaker is not properly designed, it could fail to regulate the heart correctly, which would also lead to death. Again, the mechanical ventilator is also used in hospitals and it also relies on control systems. So they regulate the airflow and pressure to support patients who cannot breathe properly on their own. So too much pressure can damage the lungs and too little won't give enough oxygen that the patient needs. So it's not just about stability, but these medical devices directly affect patient safety, hence the need for control systems.
Determine the transfer function of the given circuit. And in the circuit, we are given a 1 mega ohm resistor and a 1 microfarad capacitor in parallel, which is connected in series with a 1 mega ohm resistor connected to ground. And we have the output voltage which feeds back to the 1 mega ohm resistor.
So this is the circuit for which we are finding the transfer function. So the transfer function is simply the ratio of the output voltage to the input voltage, right? And this is our circuit. Our input voltage is E1 of T with R1 connected in parallel with the capacitance C. Then our resistance R2 also connected across the output. Right, so we first of all find the capacitive reactance of our capacitor, which we had that to be 1 on C. Right, from there we converted all our parameters to the frequency domain using Laplace transform since it has been given in the time domain. We find the combined resistance of this parallel combination, which is R1 parallel 1 on SC. Right, in finding that, we know is the product of the resistance divided by the sum of the resistance. From there, we've simplified that to have R1 divided by 1 plus S R1C. And applying the voltage divider rule, we have the R2 of S, which is the voltage at the output, right? Which is equated to R2 divided by the combined impedance of the circuit component here plus the R2 multiplying the input voltage, which is E1 of S. So this is the result of the voltage divider rule applied in this circuit.
So we have to find the voltage across the R2, which we use this formula since the ZP is in series with the R2. So we use the voltage divider rule, which will give us the R2 over the ZP plus R2, multiplying the input voltage. We just simplify it. Yeah, normal way. Then we get here, then finally, we just put our R2, which is equal to 1 mega ohms, and then C, which is equal to 1 new farad. You just input it and then mathematically, at the end, you find out that our transfer function, which is the output over the input, is equal to S plus 1 over S plus 2.
So in conclusion of the deduction, we can see that S plus 1 over S plus 2 is the function or the transfer function. So we can draw a diagram or a block diagram as moving into E2 of S. With this function, we can intuitively say that it is a higher frequency characteristic. Why? Because from the numerator we have S, and also from the denominator we have S. And also we can deduce that this transfer function is of a first class order. Why? Because the S in the function has a degree of 1. So we can conclude that our circuit here has a higher frequency characteristic, and also it has a degree of 1, making it a first order system.
I'm going to speak something small about the transfer function. The transfer function determines the relationship between an input signal and whatever comes through. So for whatever my bit numbers came to be a value, the first deduce the transfer function, which is this. So the transfer function basically tells the relationship between the input signal and whatever comes out. So that's basically what the transfer function is about and the purpose it
control
serves.
system, we have noise reduction. It removes unwanted and then fast frequency nodes to allow the slow ones to pass. Thus, it cleans the signals. We have timing circuits. The resistors and capacitors determines how fast the voltages rises and falls. Thus, it controls delay or time. We have the audio equalization. It determines the frequencies which are stronger and then weaker. Thus, it shapes the signal.
Control systems are not just equations on paper, they are part of our everyday life. For example,
think about an air conditioner. When you set it to 24 degrees, it doesn't just keep cooling endlessly. It measures the temperature and adjusts itself to maintain that set value. That's temperature control in action. In robotics, control systems help robots move smoothly without shaking or falling. If a robot's arm moves too fast or overshoots its position, it could damage what it is handling. Stability keeps it precise. And in biomedical systems, like infusion pumps or heart rate monitors, control systems regulate how medicine is delivered or how signals are processed. If these systems become unstable, it could directly affect a patient's safety. So stability analysis isn't just mathematics. It ensures safety, precision, and reliability in real-world systems.
Determine the transfer function of the circuit using classical control principles by converting the circuit into the Laplace domain and applying the impedance relationships. We showed how the output relates to the input mathematically. So the results indicate that the circuit behaves as a stable first-order system, with its response determined by the circuit's time constant. So this type of analysis is important because many engineering systems can be modeled in this way. And also, this problem demonstrates how control theory helps us predict system behavior and design reliable systems.